The first speaker afternoon is Professor Zheng from IC/MAT/CSIC, and his topic is finite time singularities for incompressible fluids. Let's welcome.
Okay, thanks for the invitation of Tsinghua, and I'm very honored to be here to talk about my recent work on finite time singularities for incompressible fluids. So all this work here is jointly done with Diego Cordova and Luis Martinez Soto. Okay, so first, let me tell you something about the equation that I'm studying, which is the incompressible oil equation. So here's the equation. U is the velocity field, so we consider U is the velocity of the fluid. So our fluid lives in 2 or 3 dimensions. So in each case, U has like 2 or 3 components. And this P is the pressure. So it's a scalar field on this Euclidean space. And F is the external force. This is the first equation is basically a consequence of Newton's second law. And the second equation is saying that the fluid is incompressible, so the flow is divergence free. And the third equation is the initial data is U naught. So this whole system models the dynamics of an ideal fluid with constant density and no viscosity. So if there is viscosity, we have a term proportional to the Laplacian of U on the right-hand side. And okay, so this in the first equation there is a pressure here, and this pressure can be expressed in terms of the velocity thanks to the incompressibility of the fluid. So if we take the divergence of the first equation, we get so this term vanishes. This is the Laplacian of P, and okay, let's just suppose that F is 0, and this is the divergence of this term. And so P can be written in terms of U via this equation. So if you solve this Laplacian equation, you can write P as a singular integral of a quadratic term of U. So this is, if you plug it back in the first equation, you get a non-local equation in terms of U. Okay, so in this way, this pressure can be eliminated, and we have an equation only in terms of U. And for this quantity of U, we have the well-known conservation of energy. Okay, if the force is 0, then it's exactly conserved. If the force is not 0, then we have the right-hand side. We have a right-hand side here. And okay, so throughout this talk, or in most part of this talk, we'll be only looking at classical solutions, which means that the solution has regularity at least C1, and the solution also has finite energy, which means that this integral of the square of U is finite. Okay, so just like for any PDEs, the first thing we look at is local well-postedness. In this case, this is a very famous equation. So local well-postedness is done almost 100 years ago by Lichtenstein and Gunther, and they showed that the equation is locally well-posed in Holder space and in Holder space. Even if we have external forcing, as long as the forcing is also in the corresponding Holder space, we have local well-postedness. And also later, local world closeness is also shown in Sobolev spaces, and this is done by Ebbing and Marsden. They proved local world closeness in HS for the classical exponent of S greater than d over 2 plus 1. Okay, this is first proved in a compact domain and then extended to the whole space. Okay, so local world closeness is known, and the next question is global world closeness, or is there a singularity? So to match the setup in local world closeness, we suppose that, okay, we have two slightly different cases. One is the Holder case. We assume that the initial data is in CK alpha and the force is in CK alpha. We want to know if there is a singularity, or we assume that the initial data is HS and the force is in HS, and we also want to know if there is a singularity. So there is a very well-known blow-up criterion, which one form of which can be stated in this way. So it says that if you first take the gradient of the velocity and you take its sup norm and you integrate it in time, okay, there should be a dt here, a ds here. If this time integral diverges when this upper limit t tends to some finite time, then there is a singularity at this capital T. So this is the, if you know some fluids, you may recognize that this is the Biel-Kato-Maeda criterion. Okay. So far, we have looked at this equation in terms of the velocity field, but actually there is a more convenient way to view this equation in terms of the vorticity. So the vorticity is defined as the curl of the velocity, and if you take the vorticity of the original equation, you almost get an equation in terms of omega in this form, but there are still some factors of u left behind, but this u can now be written, can be expressed in terms of omega using this Biot-Savart law. So this has now, okay, also notice that the pressure has disappeared because you take the curl of the pressure, it's 0. So now we have expressed or reformulated this, the order equation in terms of the vorticity omega. But here, there is a difference in 2-dimension versus 3-dimension. Notice that in 3-dimension, the term on the right-hand side is omega dot gradient of u. If you look at 2-dimension, then it is more or less equivalent to a flow that has only the x and y component, and the flow itself is independent of the z variable. Then you see that this omega is points in the z direction, but if you take the covariant derivative in the z direction, it doesn't change. So this term is 0. So it vanishes in R2. So in R2, we have one less term on the right-hand side. So this is a very important difference that leads to a key difference in 2-dimension versus 3-dimension, because in 2-dimension, this, okay, we just first just assume that the external forcing is 0. Then schematically in 2-dimension, the vorticity is just transported by the velocity, and schematically it can be written as d omega over dt is 0. So also this velocity field is divergence free. So this implies that if a scalar field is transported by a divergence-free velocity field, then all its LP norms are conserved. In particular, the sup norm is conserved. So we have a very good conserved quantity, which also which happens to be critical in true dimension. So this, together with conservation energy and other stuff, implies that, in fact, this Euler equation is globally well posed in true dimension. But this is not the case in 3 dimension, because in 3 dimension we have this right-hand side. Okay, this right-hand side, this omega, this gradient u is a singular, can be thought of as a singular integral operator acting on omega. Then schematically, the right-hand side is omega squared. Then this equation is d omega over dt is omega squared. When you integrate this, you get omega t. You can solve it explicitly, and you can see that it blows up if the initial data, if omega 0 is positive. So in 3 dimension, there is potentially a blow up, but it's not a proof. Okay, so global well-posedness in true dimension, as we see before, it is actually proven by Williamner and Holder. Okay, this Holder is the Holder in Holder space. And also, if you go through the proof, you see that the Holder norms of the velocity field grows at most at a doubly exponential rate. Okay, this is an upper bound of the growth rate, but this has been proved to be sharp in the disk in true dimension by Kiselev-Swiak in 2014. But it's still open. It's still unknown in the full plane whether double exponential growth can be attained. The Bill-Cato-Maeda criterion that we mentioned before can also be formulated in terms of vorticity, because vorticity is just related to the gradient of velocity by singular integral operator, which is almost like identity. Well, you have to be careful with the L-infinity norm, but this can be solved. This technicality can be solved. So we can also express the blow-up criterion in terms of the blow-up of the integral of the supernorm of vorticity. Okay, there is some more subtle results, like if the direction field remains Lipschitz, then there's no singularity in the full space. This is the Konstantin-Pfefferman-Maeda criterion. Okay, so far, is there any questions? Okay, so far so good. So, okay, so far is we have looked at local well-posedness, and we sort of see that global well-posedness may be not true. So we turn around and we try to look for a blow-up of solution to the Euler equation. And to simplify things, we consider axisymmetric flows. Okay, what are axisymmetric flows? First, we write everything in cylindrical coordinates. So this is in terms of r, which is the distance to the origin in the xy plane. Theta is the angle to the x-axis in the xy plane, and also the z variable. And we have ER, E theta, and EZ. There are 3 unit vectors in the direction of the cylindrical coordinates. And now the velocity can also be written in cylindrical coordinates. And this velocity field is axisymmetric if all these components are independent of the theta variable. So this geometrically, this is just saying that if you rotate the flow with respect to the z-axis, and the flow doesn't change. So if that is the case, then the flow is axisymmetric. And if the for axisymmetric flows, we have this form of the velocity, and we take the curve we get. The vorticity is also of this form. And there is also a quantity called swirl, which is simply the theta direction of the theta component of the velocity. So if the theta component is identically 0, then we say that the flow is axisymmetric without swirl. And the 3D Euler equation reduces to this very simple form. Okay, so we have the so now we try to look for blow-up in axisymmetric flows, and there are some like more or less positive numerical evidence. The first one is done in the 80s, and more recently, there is a numerical simulation done by Luo and Ho in 2014. But okay, these are numerical results, and they are not rigorous, because if you do the calculations on computers, they always carry errors. So you do not know if the blow-up is a real blow-up or just an artifact caused by the floating point error. So this is not certain. And there are some rigorous results of the blow-up, but these are all the domain of the flow are all have a boundary. So first, there is a blow-up at the boundary of from C1 alpha initial data with non-smooth boundary, and then the boundary can be improved to a smooth boundary. And finally, this is the state of the art in terms of boundary. So there is a blow-up at the boundary from smooth initial data with smooth boundary. But this result is very hard, not only in terms of analysis, but also in terms of numerics, because they used CAP, which means computer-assisted proof. So the computations and data involved in proof is huge. Like they use 2 GB or 1 GB, sorry, not GB, much lighter than that, 1 to 2 TB, terabytes of data. So such proofs are very hard to verify. And there is another group of people also constructed self-similar blow-up profiles, but they failed to prove the blow-up rigorously. And okay, and all these blow-ups are at the boundary, but almost at the same time, Ho and Huang did some new numerical simulation, and they found potential singularity in the interior. But also they cannot prove it rigorously. But now let's look at some rigorous results. The first one is done by Zheng in 2021. They proved singularity formation or blow-up of 3D Euler equation. The construction is axisymmetric without flow, but their initial data is not smooth, but only C1 alpha in this space and without force. And this alpha is sufficiently small. Okay, their construction are called exactly self-similar blow-up. So this means that if you scale things in a proper way, the solution, the blow-up does not change. And later they can, okay, but there is a catch here, because because the solution is self-similar, but it does not decay fast enough at infinity, so it turns out that the solution does not have finite energy. But later they localize the solution to a finite energy blow up also, but the initiator is still in C1 alpha. Okay, so why the initiator is only C1 alpha? Because actually it's smooth in most of the places, but it's okay. Let's draw some picture. Okay, let's say this is the z-axis, and we have the xy plane. The solution is smooth away from the z-axis and the xy plane, but it's only C1 alpha near on the z-axis, and it's only C1 alpha on the plane, on the xy plane. So this is their singularity. And there's some theoretical results saying that this alpha can at most be 1/3, but in their proof they produced the alpha very small, much smaller than 1/3. Okay, this is the result without swirl, and with swirl, Elgindi and his student Pasqualotto showed a C1 alpha blow up, axisymmetric blow up with swirl, and the blow up is on a circle. So, okay, this blow up is at the origin, but later they show a blow up like on a circle. And all these constructions are based on either exactly self-similar blow up or nearly self-similar or asymptotically self-similar blow up profile. In this talk, I will show you another and very novel construction of blow up via a cascade of vortex layers. So basically, it consists of 2 steps. The first is to find a mechanism to first put many layers of many pieces of vortices in your space, and find a mechanism in which these pieces grow. So the pieces are placed in such a manner that the next layer, the next layer is closer to the origin, and than the previous layer, and then the outside layers. You remember the Biot-Savart law? They generate a velocity field according to the Biot-Savart law, and you can arrange the next layer in such a way that the Biot-Savart law causes the growth of the next layer via the vortex stretching term. You remember, in 3 dimensions there is a term called a vortex stretching term, and you can use it to cause the growth of the next layer. And but there's also the self-interaction of the layer. You want that to be small or to be ignored. Then we can use a gluing argument to combine an infinite number of these layers to get this infinite sum, and you call this our actual vorticity, and it turns out that it's the vorticity of a blow-up solution. So more specifically, we consider we had 2 different scenarios. One is the blow-up for axisymmetric flows without swirl from initial data that is smooth everywhere except at the origin. So this is better than this. Here it's improved to infinity. Okay, this is the initial data. The initial data here on this plane, it's also improved to infinity, but it's only C1 alpha at the origin. Okay, and without forcing. And the second scenario is blow up for non-axis symmetric flows with a dissipation. So if your dissipation is like from is physically corresponds to physical loss, then it's like Laplacian or minus Laplacian of u. This is the corresponds to true derivatives u, but we cannot exactly reach that. What we can reach is like this number. This is roughly 0.1 order of derivatives of u. We have this dissipation of this strength. And the blow up, but now the initial data can be smooth, and the force is C1 is better than C1. So locally, in such a space, we have local well postness. So this is this blow up is like a global blow up. Okay, I'll go into that later. So here I only say that the force is like in this space, but later I will exactly tell you how we actually construct the force. Okay, the force is actually also constructed by us. So we construct, okay, in this result, the velocity is constructed by us, and the force is 0. In this result, the velocity and the force are both constructed by us. So here's the exact statement of the first result. Okay, we have unforced 3D order blow up from this initial data, and the vorticity grows like 1 over t. Okay, one important thing is that the blow up is not self-similar. So this we have more flexibility than this self-similar profile constructed by Zheng. But after our work came out, Chen showed that actually you can modify Zheng's construction a little bit to also get blow up from only one singularity. But that's on top of Zheng's argument, on top of Zheng's proof, which is already very long, but our proof is very short. And our blow up rate of the vorticity is 1 over t. This is like the borderline of the Biot-Kato-Maeder criterion, but it is consistent with that criterion. And the Holder exponent, okay, unfortunately it's still very small, but we think it's better than Zheng's Holder exponent. But it's still an open problem whether we can reach the 1/3 threshold of to match the previous local well postness result. Okay, so here is what our construction looks like. So this is a this is actually two-dimensional projection of the three-dimensional velocity field. So okay, sorry, this is not velocity field, but vorticity. So this is pointing out, this is pointing in, and these large ones are like, let's say the first vortex layer, and the small ones are the second vortex layer. And the first vortex layer generates a velocity field like this. It's a saddle point near the origin, and it's flowing this way. So it causes a gradient of the velocity that, according to the vortex stretching term, actually makes this inner layer grow. So this orientation of the vortex layers has been aligned so that this actually causes the inner layer to grow. Okay, so more specifically, how do we actually quantify the growth rate? We let xn be the strength of the nth vortex layer, and let this big Wn to be the profile, renormalized profile of the vortex layer, so that the nth vortex layer is xn times capital Wn. Then, okay, this is the strength. Then the strength xn actually satisfies this ODE. You see that actually this ODE is saying that the growth rate of xn is proportional to the strength of all previous layers, and this ODE can be solved. And there is a particular solution. Okay, we can actually solve this equation, this ODE system backwards. So there we found a solution that at time 0 is actually growing exponentially, but at negative time it's actually decaying to 0. So when we run backwards, or actually run forwards in time, we're actually growing from this to this. So this is actually a blow up. Then we first we take a finite sum of n, big N, vortex layers. Then this is actually smooth because we have a finite sum, and this each profile, this can be assumed to be smooth, and we get a smooth axisymmetric flow without swirl, and this is well-posed. This has global well-posedness. This is a classical result, but we want an energy estimate that is uniform in this big N. Then we can take big N to infinity, and this limit is smooth away from the origin, and this limit is a solution to the Euler equation in its vorticity form. And this this estimate of xn t, actually this decays exponentially. So xn t decays exponentially at negative time, but grows exponentially at time 0. This translates to Holder continuity in the initial data, but a blow up in the supernorm of this omega at time 0. And the rate of blow up can also be quantified as 1 over t. Okay, so this is the sketch of the proof for the first theorem. The second theorem, so we also have a construction by infinitely many layers. But these layers are like sinusoidal planar waves with low frequency layers corresponding to outer layers and high frequency layers corresponding to inner layers. And the low frequency layers produces the velocity generated by low frequency layers produces a growth in high frequency layers. But these layers are not activated at the same time. Initially, there is only a layer. Initially, there is only one layer, that is the outermost layer. But then later, we activate these inner layers, and they grow. Then they grow according to the velocity generated by the outer layers. And at time big T, we have blow up. So specifically, we want our velocity to generate, we want our vorticity to generate a velocity of this form. So it's also a saddle point near the origin. So if we add an inner vortex layer of this form, then the naive or like approximate evolution equation for the added vorticity is like this. So this only the first component is relevant, and this is its evolution equation. And if we choose omega 1 such that this main term vanishes, actually, fortunately for us, if we choose omega 1 to be a planar sinusoidal wave, then the main term actually vanishes. Then we are only left with this equation, which can be solved explicitly to to see that the omega 1 actually grow. And also this the velocity generated by omega 1 is of this form, and this velocity field is very similar to this velocity field, but with a direction switched. So if we switch the direction of the next layer accordingly, we can iterate this construction ad infinitum to get a sum of infinitely many vortex layers. So, but now we come to the choice of our force, because in this process there are many errors that we are ignoring, like because everything is like hand waving and very approximate, and the force is introduced to just cancel this error made in the process. And like here we say that some error, we kill some of the error using the force. But we also have the constraint of force such that it must be divergence free. So this is non-trivial. The cancellation is non-trivial. And also there's the self-interaction of the innermost layer, which, because the innermost layer is has very high frequency, and the self-interaction potentially is very big. But if we choose a sinusoidal wave, the main term actually is 0. So we also get a small error that can be canceled by the force. Okay, so this is the exact form of the vortex layers. We have oscillation in two directions and a cutoff in all the directions. And this is the main component, and we have another component that whose purpose is to make this vorticity divergence free. And then we can use the Biot-Savart law to compute the velocity generated by the vorticity. It's indeed a saddle point. So it expands in xn plus 1 direction and shrinks in xn plus 2 direction. Okay, all these subscripts are interpreted modulo 3. Then if we put a new layer, we switch all the directions by 1. So we have oscillation in xn plus 2 and xn plus 3. But the main component is in the xn plus 1 direction. Then, because this velocity expands in the xn plus 1 direction, so if you look at the so the vortex stretching term actually stretches this omega n. Okay, now we play the old trick of taking this infinite sum. Then each vortex layer satisfies. As long as each vortex layer satisfies this equation, this un is the velocity generated by previous layers, then this infinite sum is a solution of the Euler equation. Okay, so here we have in this equation we have no dissipation, but we can add dissipation. And the dissipation is of this form, like this is, okay, this is alpha ordered of derivatives. And there are two related results. The first one is when alpha is smaller than this number, which is about 0.1, we have a blow up with a forcing in better than C1. But there is a second result to appear, or it's a work in progress. If we extend this alpha to some number that is larger, that is 2/7, which is approximately 0.3, then we can blow up in a slightly different space, which is C1 minus alpha plus. Okay, this is a space that actually has local well-postedness of this equation, but this is not proved in the literature. We have to prove it ourselves. So for that's all for my lecture, and thanks for listening.